You know, when you look in the mirror in the morning, there is this profound illusion of solidity, right?
Absolutely. You see this solid thing,
Yeah, you see your skin, your hair, the shape of your muscles, and you just think to yourself, that's me. Like, I am a solid, finished, static structure.
right? A completed project.
Exactly. But if you were to somehow zoom in, like past the tissues, past the individual cell walls, you would find that you aren't really a solid object at all.
Not even close.
I mean, you are in reality a wildly chaotic, nonstop construction site.
A completely relentless one at that. It's just billions of tiny, intricate components being assembled, disassembled, folded, and transported like every single second.
Every single second.
Yeah, just to keep that illusion of a solid you intact, you're essentially rebuilding yourself on a microscopic level constantly.
Exactly. And that brings us to the mission of today's deep dive. We are going to decode the biological alphabet that makes up everything from, your heart muscle to the hair on your head.
Down to the life-saving drugs used in modern hospitals, actually.
Right. We are going to look at the literal chemical bricks that build life, how your body acquires them, and what happens when the entire system is pushed to its absolute limits.
It really is the ultimate backstage pass to your own biology. We are moving past the macro level, the organs and bones we all learn about in grade school, and diving into the fundamental machinery.
Okay, let's unpack this, because before we even look at the physical structures that make up the human body, I want to start in a very dramatic place.
Oh, okay. Where are we starting?
I want to drop us right into the most critical state of the human machine, a medical emergency. Let's talk about intravenous or IV therapy.
Ah, right. The front lines of medicine.
Exactly. When someone is in trauma, the very first thing that happens in the ER is that they get hooked up to an IV drip. And a common solution used is a dextrose mixture, which contains approximately 170 calories of pure energy.
But absolutely zero natural electrolytes.
Right, zero. The medical professionals have to add those electrolytes manually, according to the specific requirements of the patient. And this is all delivered directly into a vein.
And that delivery mechanism is just crucial. The IV drip is the absolute fastest way to deliver fluids, electrolytes, and medications throughout the entire body.
Because it skips all the usual filters, right?
Exactly. It is a highly engineered system, and it is specifically designed to prevent air from entering the bloodstream, which, as we'll get into, is a matter of life and death.
Right. And when I think about this, I picture the IV like a VIP express lane for the body.
A VIP lane, I like that.
Yeah, because normally if you drink water or eat food, it has to go through the incredibly slow, winding traffic jam of the digestive system.
No, that takes hours.
Right. It has to hit the stomach acid, go through the intestines, get processed by the liver. But the IV drip just kicks down the door and puts the good stuff right onto the main highway.
It really does.
But I do have to push back a little on this dextrose mixture. I mean, if it's just 170 calories of pure energy with absolutely no electrolytes in it initially, isn't it basically just highly sterile medical sugar water?
Well, chemically speaking, yes.
So why start with that? If they are dehydrated, why can't we just pump something like, I don't know, Gatorade or a sports drink directly into their veins?
Oh, wow. Well, if you pumped a commercial sports drink directly into someone's veins, you would likely kill them very quickly.
Wait, really? Killed it?
Very quickly. And the reason why comes down to a concept called osmolarity. Your blood has a very specific concentration of dissolved particles, salt, protein, sugars.
Okay.
This is its tonicity. The fluid inside your red blood cells has to perfectly match the fluid outside in the blood plasma.
Because if it doesn't match, water starts moving to try and balance it out, right?
Precisely. It's osmosis. If you inject a fluid that is hypotonic, meaning it has far fewer dissolved particles than your blood, like pure water, the water will rush into your red blood cells to try and dilute the higher concentration of salts inside them.
And what happens then?
The cells will swell up like balloons and literally explode. It's called lysis.
Oh my God.
Yeah. Conversely, if you inject something incredibly salty and concentrated, water will rush out of the cells, causing them to shrivel up and die, which is called crenation.
Okay, so that explains why you can't just use water or a sports drink. The fluid going directly into the vein has to be a perfect osmotic match.
It has to be isotonic.
Isotonic, right?
Exactly. And that dextrose solution, usually a 5% dextrose in water solution, is isotonic when it enters the body. And dextrose is chemically identical to glucose, which is the exact form of sugar that your body's cells use for energy.
But 170 calories doesn't sound like a lot. I mean, that's like what? A handful of almonds? A can of soda?
Roughly, yeah.
Why bother with such a tiny amount of calories in an emergency?
It's all about the concept of baseline survival. When a patient is in a state of trauma, shock, or severe dehydration, their cells are crying out for immediate, readily available energy just to keep the basic metabolic engines running.
Just to keep the lights on.
Exactly. The brain alone consumes an enormous amount of glucose every hour just for basic function. That 170 calories, when delivered instantly and continuously into the bloodstream, provides a steady baseline fuel source for the central nervous system and the heart.
Bypassing the digestive system entirely.
Right, meaning the body doesn't have to expend precious energy trying to break down food while it's already fighting to survive.
So it's not about feeding them a full meal. It's about giving the factory just enough power to keep the emergency generators running.
That's a perfect way to look at it.
Yeah.
But your point about the electrolytes is the next critical layer because it highlights the profound precision of modern medicine. Hydration and resuscitation are absolutely not a one-size-fits-all process.
Right. The source said they are added according to requirements.
Exactly. The medical professional has to custom mix the electrolytes, the sodium, potassium, calcium, and chloride, based on exactly what that specific patient has lost.
Because electrolytes aren't just for, like, muscle cramps after a run. They're the electrical grid of the body, right?
They are the literal charged ions that allow your nervous system to communicate. They dictate the electrical gradients across your cell membranes.
So every time my brain tells my arm to move.
When a nerve fires a signal to tell your heart to beat or your arm to move, it's doing so by rapidly pumping sodium and potassium ions back and forth across the cell wall.
Wow.
So if a patient comes into the ER having lost blood, they require one specific balance of these ions to restore their blood volume. If they are severely dehydrated from prolonged illness, they might have an excess of sodium, but a dangerous lack of potassium.
So the doctor has to act as a real-time biochemist.
Yes, tuning this incredibly complex internal ocean while the patient's system is already failing.
And the physical delivery of this custom cocktail is fascinating to me. Bypassing that digestive traffic jam relies entirely on physics.
It does.
The IV bag hangs on a pole above the patient, and it relies on hydrostatic pressure. Gravity pulls the fluid down the tube, creating enough pressure to overcome the natural blood pressure inside the patient's vein, gently forcing the fluid into the closed circulatory loop.
A closed, pressurized loop. Which brings us to a major vulnerability. The design of the IV system is meticulous about preventing air from entering the bloodstream.
Yes, I really want to dig into that because we always see it in medical dramas, right? The nurse taps the syringe, pushes a little fluid out the top, or rigorously primes the IV tubing to make sure there are absolutely no air bubbles.
The standard procedure, yes.
But what actually happens if they fail? I mean, if you swallow a pocket of air while eating, you just burp. It's harmless. Why is a bubble of air in the VIP express lane a catastrophic event?
Because your digestive system is essentially a tube that is open to the outside world at both ends. Air can enter and exit freely. But your circulatory system is a strictly liquid-only environment. If a significant amount of air enters a vein, it travels along with the blood flow toward the heart. This creates what is called an air embolism.
Now, an embolism usually means a blockage, like a blood clot, right? But air isn't solid. How does air block anything?
This is where we have to look at the physics of liquids versus gases. Liquids, like blood, are basically incompressible.
Meaning you can't squish them down?
Right. When your heart, which is a muscular pump, squeezes, it forces the blood out of the chamber and into the lungs of the body. It operates on the physical principle that if you squeeze a container full of liquid, the liquid has to go somewhere.
Like squeezing a water balloon, the water just shoots out.
Exactly. But gases, like air, are highly compressible. Imagine your heart's right ventricle pumping away. Suddenly, a large pocket of air arrives from that faulty valve line.
Okay, I'm picturing it.
The ventricle fills with a mixture of blood and this air. When the heart muscle forcefully contracts to push the blood to the lungs, instead of the blood moving forward, the air bubble simply compresses.
It just squishes down.
It absorbs the force of the contraction entirely.
Oh, wow. So the pump basically loses its grip.
It's called an airlock. The blood and air get churned into a frothy mixture inside the heart chamber. Because the air keeps compressing and expanding with every heartbeat, the physical forward movement of the blood drops to zero.
The pump stalls.
The pump stalls. Without blood moving to the lungs to get oxygen, and without oxygen reaching the brain, the entire system faces catastrophic failure within minutes.
That is terrifying. The heart is literally just squeezing empty space, churning up a froth instead of pushing blood.
It really highlights how delicate the balance is.
It makes you realize how fragile the system is, but also how refined our medical technology has become. I mean, we've mastered the art of hacking this pressurized internal highway to deliver custom fuels and electrical grids safely directly to the cells.
And that perfectly sets up the next massive question for this deep dive. We know how we deliver vital fluids and energy to the cells. But what are those cells actually made of? What is sitting at the end of that 5E line, receiving all that dextrose and custom mixed fluid?
Which shifts us from the delivery mechanism to the architecture of life itself. If water and electrolytes are the environment, the structural reality of the body comes down to proteins.
Yeah, proteins.
And the statistics on this completely changed how I visualize the human body. We always hear that humans are roughly 60% to 70% water, right?
Mostly water, yes.
But if you take a living cell and you magically remove all that water, you are left with what biologists call the dry weight. And roughly 50% of the dry weight of a human cell is pure protein.
What's fascinating here is that 50% figure, half of your solid mass. This is a staggering statistic when you pause to visualize it.
It really is. Here's where it gets really interesting for me. If a living cell is a house, proteins aren't just the bricks. They are the wooden framing, the drywall, the roof tiles, the floorboards, the doors, and the paint on the walls.
They are everything.
They are the bulk of the non-bony structures of our bodies. They make up our muscles, our skin, our hair, our nails. And it's not just us. Hold on, this is the part from the source that I found so incredible. My hair, a bird's feather, a sheep's wool, a rhinoceros horn. They are all fundamentally made of the exact same chemical family of proteins.
They are. We often think of ourselves as, biologically distinct from other animals, but chemically, we're all shopping at the exact same hardware store. The structural unity of life on Earth is just profound.
So let's look at the inventory of this hardware store. What actually is a protein? If we break it down into its elemental atoms, we're looking at carbon, hydrogen, oxygen, nitrogen, and frequently sulfur.
And that specific list of elements is the key to everything. The first three, carbon, hydrogen, and oxygen, are the backbone of most organic matter. If you take just those three, you can build carbohydrates like the dextrose we were just talking about, and you can build lipids or fats.
Which are mostly used for energy storage, right?
Right. Carbon is fantastic at forming long, stable chains. It's the lumber. But carbohydrates and fats, structurally speaking, are relatively simple. They are largely linear, or they form simple rings. They are fuels and boundaries.
Okay.
But the moment you introduce nitrogen into that molecular mix, the complexity explodes. Proteins are highly complicated nitrogenous compounds.
So why does nitrogen change the game so much? What makes it the magic ingredient?
It comes down to atomic valency and electron pairs. Carbon wants to form 4 bonds, which makes it a great intersection. But nitrogen wants to form 3 bonds, and it carries what is called a lone pair of electrons.
A lone pair.
Yeah, 2 electrons that just sit on the atom, not bonded to anything else. This lone pair is highly electronegative. It carries a negative charge. Because of this, it can form what are called hydrogen bonds with other parts of a molecule that have a slight positive charge.
So it's like tiny microscopic magnets built into the structure.
Precisely. Nitrogen allows these massive molecular chains to fold, twist, and magnetically stick to themselves in incredibly complex, three-dimensional origami-like shapes.
Wow.
If carbon, hydrogen, and oxygen are the wooden beams of the house, nitrogen provides the specialized hinges, brackets, and joints that let you build a vaulted cathedral ceiling instead of just a flat deck.
And what about the sulfur? You mentioned hair and wool and feathers. Where does sulfur fit into this cathedral?
If nitrogen is the hinges, sulfur is the heavy-duty structural welding. Certain building blocks of proteins contain sulfur atoms. When 2 sulfur atoms from different parts of a protein chain get close to each other, they can form a covalent bond called a disulfide bridge.
A disulfide bridge.
Yes, this is an incredibly strong physical link. It anchors the folded protein in place so it doesn't unravel.
So this is why skin and hair and feathers are so tough.
Exactly. The toughness of a rhino's horn, the durability of a sheep's wool, it's all heavily reliant on these disulfide bridges. In fact, if you've ever known someone to get a perm to permanently curl their hair, what the hairdresser is actually doing is applying a chemical that temporarily breaks the sulfur bonds in the hair proteins.
Wait, really?
Yeah, the hair is reshaped on curlers, and then a neutralizer is applied to reform those sulfur bonds in the new shape. You are literally doing structural biochemistry on your head to rearrange the disulfide bridges.
That is wild. You're chemically re-welding the structural steel of your hair.
Exactly.
Okay, so we know the elements. carbon, hydrogen, oxygen, nitrogen, sulfur. But these atoms don't just float around randomly, they are organized into specific building blocks. If we take that 50% structural mass, that desiccated cathedral, and put it under an incredibly powerful electron microscope, what are the actual bricks made of?
We're looking at what chemists call polymers of amino acids. A polymer is simply a massive molecule made up of many repeating smaller units called monomers.
Like a heavy metal chain made of individual links.
Yes. And those individual links are the amino acids. These are the fundamental units of biological architecture. Every amino acid is an organic compound consisting of three main parts organized around a central carbon atom.
Let's visualize this. The central carbon is in the middle. On one side, you have the amino group. This is where the nitrogen lives. It's one nitrogen atom bonded to two hydrogen atoms, so NH2OVO2.
Correct. And on the exact opposite side of that central carbon, you have the carboxyl group. This is a carbon atom double bonded to an oxygen atom and single bonded to a hydroxyl group, which is an oxygen and a hydrogen. It's written chemically as two games.
So you have the NH2 on the left, the central carbon in the middle, and the seroquols on the right. And then attached to that central carbon is a mysterious third component called the side chain, or the R group. And in biology, according to the source, there are exactly 20 different R groups, meaning there are 20 different amino acids in total.
This specific molecular arrangement is perhaps one of the most elegant foundational concepts in all of science.
So what does this all mean? When I try to visualize this formula, the amino group, the carboxyl group, and this variable R group, I immediately think of a standard Lego brick.
A Lego brick, okay.
Yeah, for anyone trying to picture this in their mind, imagine a classic rectangular Lego. It has the little plastic bumps on the top and the hollow receiving tubes on the bottom. Those interlocking parts are universal. They are always exactly the same on every single brick. They have to be, otherwise the Legos wouldn't snap together into a stack.
The top and bottom are the standard docking mechanisms.
Right. In our amino acid, the amino group, the NH2 and the carboxyl group, the COAO, are the universal top and bottom of the Lego brick. They are the standard structural backbone. They are identical on all 20 amino acids.
Right.
But the R group, that is the unique accessory you snap onto the side of the Lego. Maybe the accessory is a tiny wheel, maybe the little steering wheel, maybe it's a clear window pane. The base block is the same, so it perfectly snaps into the growing chain. But the side piece gives that specific link a totally unique function.
That is a phenomenal analogy. And the profound implications of having a universal structural backbone is that any amino acid can connect to any other amino acid. An amino acid with a wheel can snap onto one with a window. They just link together end to end endlessly. But because of those variable R groups hanging off the side of the chain, the resulting polymer isn't just a boring, straight piece of string.
Because all those tiny molecular magnets and accessories are interacting with each other.
Exactly. Let's look at those 20 R groups. Some of them are as simple as a single hydrogen atom. Some are massive, bulky ring structures. Some carry a strong positive electrical charge. Others are negatively charged.
It's a huge variety.
It is. Some are highly hydrophilic, meaning they absolutely love water and want to push toward it. Others are hydrophobic. They are essentially molecular oil. They hate water and violently repel it.
And remember, this entire chain is floating in the water-based ocean of the cell.
All right, so imagine a chain of thousands of these Legos floating in water. The hydrophobic R groups panic. They want to get away from the water, so they fold inward, clumping together in the center of the structure to hide. The hydrophilic R groups push outward to interact with the water. The positively charged R groups act like magnets, reaching across the chain to stick to the negatively charged R groups.
So the chain instantly crumples and contorts itself.
It snaps into a highly specific, complex, three-dimensional shape. This is called protein folding, and it happens in milliseconds. And the golden rule of biology is this: shape dictates function.
Shape dictates function.
If the chain folds into a hollow microscopic tube, it becomes a channel in a cell wall that allows specific nutrients to enter. If it folds into a tough, braided rope, it becomes the keratin in your hair or a rhino's horn. If it folds into a highly complex globule with a tiny, perfectly oxygen-sized pocket in the center, it becomes hemoglobin, the protein in your red blood cells that carries oxygen from your lungs to your brain.
That is absolutely mind-bending. All of that staggering diversity, from the hemoglobin keeping us alive, to the structural fibers of our muscles, to the feathers of an eagle, is created simply by changing the sequence of just 20 different variations of this R group. 20 Lego accessories.
It is a biological alphabet.
Hmm.
Just as the English language uses only 26 letters to write every play by Shakespeare, every technical manual, and every text message ever sent, nature uses just 20 amino acids to write the entirety of the animal and plant kingdoms. If you arrange the letters differently, you get a different word. If you arrange the amino acids differently, you get a completely different protein.
And the precision required is terrifying. I was reading recently about sickle cell anemia. That entire life-altering disease is caused by a spelling error in this alphabet.
It is the perfect example. Hemoglobin is made of hundreds of amino acids.
Right.
In sickle cell anemia, just one of those amino acids, one single Lego brick out of hundreds, is swapped. A hydrophilic amino acid is accidentally replaced with a hydrophobic one.
So it folds wrong.
It folds wrong. That single hydrophobic patch tries to hide from water by sticking to another hemoglobin molecule, and they chain together into long, rigid rods inside the red blood cell. It deforms the entire cell into a sickle shape, causing it to block blood vessels. The change of a single R group alters the physics of the entire circulatory system.
Which just really underscores how critical these 20 specific building blocks are. Every single one has to be perfectly available. And this naturally leads to the next big question. If we absolutely need these 20 exact Lego bricks to build and maintain the cathedral of our body, where does the human factory actually get them?
The internal economy of the human body sources these materials in two very distinct ways. We divide the 20 amino acids into two categories based on how we acquire them. 10 out of the 20 amino acids can be synthesized internally by the human body.
Okay, so we make them ourselves.
Right. Our cells take raw materials and construct them from scratch. Biologists call these non-essential amino acids. The other 10 cannot be synthesized by our bodies under any circumstances. They are called essential amino acids, and they must be supplied entirely through our diet.
Okay, I have to push back hard on the scientific naming convention because to anyone outside a biology lab, it sounds completely backward.
Oh, absolutely. It confuses everyone.
Let's think about this. If I need a specific amino acid to literally build my heart tissue, and my body's internal factory takes the time to brilliantly manufacture it from scratch every single day to keep me alive, how on earth is that non-essential? If they're building blocks of life, aren't they all essential? Calling the 10 miraculous compounds our body produces non-essential just feels like terrible marketing.
You are definitely not the first person to have this reaction. The terminology is highly counterintuitive when you look at it from the perspective of cellular function. If we connect this to the bigger picture, every single one of the 20 is biochemically essential for life.
I mean, I'm sitting here right now, and without me even consciously thinking about it, my internal organs are pulling carbon and nitrogen out of my bloodstream and synthesizing 10 completely different, complex molecular structures just to repair the micro tears in my muscles from yesterday's workout. It's a miracle of silent manufacturing.
It is a profound metabolic feat. But the scientists who named them were looking at it purely from the perspective of dietary intake and nutritional science. Essential doesn't mean it's important for cellular life. It means it is essential that you put it in your mouth and swallow it. It is a dietary imperative.
Because if we don't eat them, the factory doesn't just slow down, it completely halts. We can't build the proteins and we die.
Exactly. If your body is trying to build a protein that is 1,000 amino acids long, and the 500th link requires an essential amino acid that you haven't eaten, the whole assembly line stops. The protein cannot be finished. But your pushback touches on one of the most fascinating evolutionary mysteries in human biology. If these 20 amino acids are the absolute alphabet of life, why on earth would evolution leave us unable to produce half of them?
Yeah, that seems like a massive, glaring design flaw. We are walking around with $1 million manufacturing plant that's missing half the blueprints. If we evolved to be the apex predators, why didn't we evolve to just make all 20 and be completely self-sufficient?
It does seem like a flaw, until you view it through the lens of biological economics and thermodynamics. Synthesizing amino acids from scratch is incredibly energy intensive. It requires complex metabolic pathways, dozens of highly specific enzymes acting in sequence, and a massive amount of cellular energy, usually in the form of ATP.
Okay.
The 10 essential amino acids, the ones we can't make, tend to be the ones with the most complex, bulky, and difficult-to-build side chains. Building those intricate ring structures takes a lot of work.
It was a massive drain on the body's resources.
A huge drain. And over millions of years of evolution, our ancestors were constantly surrounded by a biosphere, plants, fungi, and other animals, that already contained these complex amino acids.
Oh, I see. We outsourced the labor.
Exactly. Evolution basically did a ruthless cost-benefit analysis. Why should the human body expend massive amounts of its own precious daily energy maintaining the complex enzymatic machinery required to build these 10 difficult amino acids from scratch, when we can just reach out, eat a leaf, a handful of berries, or a piece of meat, and steal the perfectly assembled amino acids that the other organism already spent its energy building?
Wow. We lost the ability to make them because we simply didn't need to. The global food web provided them for free, and we used that saved energy to build bigger brains.
Precisely. We traded biochemical independence for metabolic efficiency. But it means we are permanently tethered to the rest of the biosphere. Plants are the true master chemists of the planet. They have symbiotic bacteria in their roots that can pull inert nitrogen gas right out of the atmosphere, something we cannot do, and they use it to synthesize all 20 amino acids from scratch.
And then animals eat the plants and incorporate those acids into their muscles.
Right. We eat the plants and the animals. Your microscopic cellular chemistry, the very structures keeping you alive, are directly physically dependent on the macro-level global food web.
That completely flips how I look at a meal. When I sit down to eat dinner, I'm not just getting amorphous calories or raw energy like the dextrose and the trauma bayfi. I am literally going to the biological hardware store, walking down the aisles and acquiring the 10 specific structural Lego pieces. My own internal factory forgot how to manufacture. I am eating the alphabet I need to write my own genetic code into physical reality.
That is exactly what you're doing.
Okay, so we have the bricks. We know we quietly manufacture 10 of them ourselves, and we scavenge the other 10 from the plants and animals we consume. Now, we need to look at how the body actually assembles the wall. We have thousands of free-floating amino acids in the cell. How do we snap them together? What is the actual mechanism of linking the Lego bricks?
This is where we look at the formation of what biologists call the peptide bond, or peptide linkage. This is the permanent, covalent chemical bond that joins the carboxyl group of one amino acid to the amino group of the next.
And the specific chemical reaction that creates this bond is brilliant, but also highly ironic. We started this deep dive talking about 5E drips, which are literally designed to pump fluids and hydration into the human body to save its life. Water is the solvent of life. But to actually build the permanent solid structures of the body, to build the proteins that make up our heart and our bones, the body has to aggressively extract water from the molecules.
Yes, the process of building a protein is literally called dehydration synthesis.
It is a beautiful paradox. Let's visualize the biochemistry to understand why this dehydration has to happen. Imagine our two Lego bricks floating in the fluid of the cell, sitting side by side. On the right side of the first amino acid, you have the carboxyl group. That's a carbon atom, 2 oxygen atoms, and a hydrogen atom. And on the left side of the second amino acid, facing it, you have the amino group, NH2 2s. 1 nitrogen atom, 2 hydrogen atoms.
So they are bumped up against each other, but they are both stable, their outer electron shells are full, they don't want to react.
Right. They are perfectly happy as they are. To bond these two massive molecules together into a chain, the body needs to forcefully create open, highly reactive docking ports on both molecules.
Yes.
I think of this like 2 pieces of extremely strong, double-sided sticky tape. But right now, both pieces of tape have that smooth, protective paper backing on them. You can press them together all you want, but they won't stick because the paper is in the way.
That's a perfect way to look at it.
Yeah.
The protective paper is made of specific atoms. To get them to stick, a microscopic machine in the cell, an enzyme called a ribosome, acts like a precise mechanic. It grabs both amino acids, it reaches into the carboxyl side of the first molecule, and violently plucks off a hydroxyl group.
A tetroxyl group.
That's an oxygen and a hydrogen bonded together, an O' group. It rips off the protective paper.
Okay, so the carbon on the first molecule is now exposed and highly reactive. It's looking for a partner.
Exactly. Then the ribosome reaches into the amino side of the second molecule, and it plucks off a single hydrogen atom and all dollars. Now the nitrogen on the second molecule is exposed and highly reactive.
Wait, let's look at what the mechanic just threw away. It ripped off an all dollars from the first one and an dollar from the second one. 2 hydrogens and 1 oxygen. That's 2/3 and 2 allers.
That is water. By chemically tearing a water molecule out from between the 2 amino acids, the exposed carbon and the exposed nitrogen instantly grasp hands to stabilize their electron shells. They slam together, forming a remarkably strong, permanent covalent bridge. That bridge is the peptide linkage.
Incredible.
And the byproduct of this biological welding, the trash thrown away from ripping off the tape's backing, is a brand new, free-floating water molecule.
That is absolutely incredible. The body is essentially welding these pieces together, and the spark that flies off the welder is a literal drop of water. But what about the scale of this operation? We talked about hemoglobin being a few hundred amino acids long, but structurally, proteins can be massive. Just how massive and tangled do these molecular chains get?
The scale is almost hard to comprehend. To give you some context, insulin, a very small protein hormone that regulates your blood sugar, is only 51 amino acids long. Hemoglobin is around 574 amino acids long. But when we talk about structural proteins, the chains are immense.
How big are we talking?
Take titin, for example. Titin is a protein that functions like a molecular spring in your muscle tissue. It gives your muscles their elasticity so they don't tear when you stretch. Titin is the largest known naturally occurring protein. It could be over 34,000 amino acids long.
34,000 pieces long in one single continuous chain.
Yes, 34,000 Legos snap together perfectly in sequence, and every single linkage along that immense sprawling chain was formed by this exact dehydration synthesis process.
That's exhausting to even think about.
The cellular machinery had to sequentially grab 34,000 amino acids, strip away 34,000 molecules of water, and weld the peptide bonds one by one. And as it's being built, the chain is simultaneously contorting and folding into that precise 3D spring shape based on the hydrophobic and hydrophilic R groups.
All happening silently, millions of times a second in our muscles right now. It's dizzying. But if dehydration builds the chain by removing water, how do we break it down? Because earlier we talked about eating proteins to get the essential amino acids.
There's the dietary imperative.
If I eat a piece of chicken, that chicken muscle is made of proteins that are tens of thousands of links long. How does my body take that massive chain and turn it back into the individual 20 Legos so I can absorb them?
It uses the beautiful symmetry of biochemistry. The process is the exact reverse, and it is called hydrolysis.
Hydro meaning water, and lysis meaning to split or break apart.
Exactly. When you eat a protein, it travels down to your stomach and intestines. Your digestive system releases enzymes, along with highly acidic fluids. These enzymes act like molecular crowbars. They aggressively force water molecules back into the peptide bonds.
So they are essentially shoving the protective paper backing right back onto the sticky tape.
Yes. By forcing the H2R back into the structure, the covalent bond shatters. The hydroxyl group, the O-DARL reattaches to the carboxyl side, the hydrogen reattaches to the amino side, and the massive 34,000 link chain breaks apart link by link, returning to 34,000 individual free-floating amino acids.
Wow.
Your intestines absorb these single Legos into your bloodstream, they travel to your cells, and your own ribosomes use dehydration synthesis to weld them back together into human proteins. Water is the master key. It locks the structure together by leaving, and it tears the structure apart by entering.
So we've looked at this microscopic chemistry in intense detail. We've seen how the body uses the IV physics to fuel the factory, how the amino acid alphabet is structured with its universal backbone and unique R groups, where we scavenge the essential ones from the global food web, and how the mechanics of dehydration synthesis weld them together. Now, for the final section of our deep dive, I want to zoom all the way out.
Let's do it.
Because this fundamental alphabet doesn't just exist in our cells. It dictates human industry, modern medicine, and our daily interactions with the world. Let's look at the manifold macro uses of proteins.
This is where the sheer versatility of that 50% dry weight becomes apparent in our everyday lives.
We've touched on the first major use, the food web. We eat the protoplasm of animals, meat, fish, eggs, and the proteins of plants, beans, pulses, nuts, to acquire our essential building blocks. But the second major application completely blew my mind. We often think of proteins just as structural stuff, the wooden bricks of the house.
Right, just static building materials.
But there is a whole class of proteins called enzymes. We always hear about enzymes in digestion, or in yogurt, helping break down a heavy meal. But this source says they are used as drugs to treat blood cancer. That is incredible. How does a protein chain fight cancer?
This raises an important question, and it requires us to look at what an enzyme actually does. An enzyme is a protein that acts as a biological catalyst. In chemistry, a catalyst is a machine that speeds up a chemical reaction without being consumed by it. We just talked about hydrolysis and dehydration synthesis.
Right.
Without enzymes acting as the mechanics to physically grab the molecules, bend them, and lower the energy required to make them react, those processes would happen so incredibly slowly that you would die before you could digest a single meal or build a single muscle fiber.
So enzymes aren't the bricks, they are the power tools of the cell.
They are microscopic power tools. And remember the golden rule: shape dictates function. Because enzymes are proteins, they fold into highly specific 3D shapes. They have what is called an active site, a small pocket that perfectly matches the shape of a specific target molecule, like a lock and key. An enzyme designed to break down milk sugar will only fit milk sugar. It will ignore everything else in the body.
So how does this extraordinary specificity translate to a cancer drug?
It's one of the most brilliant hacks in medical history. Let's look at a drug called asparaginase, which is used to treat acute lymphoblastic leukemia, a type of blood cancer. Normal, healthy human cells can synthesize an amino acid called asparagine. It's one of the non-essential ones our internal factory can make from scratch.
Okay, so our healthy cells have plenty of it.
Right. But these specific leukemia cancer cells have a genetic mutation. Their factory is broken. They cannot synthesize their own asparagine. In order to rapidly divide and grow the tumor, the cancer cells have to steal asparagine from the patient's bloodstream.
They are heavily reliant on the blood supply to deliver this specific Lego block.
Exactly. So medical scientists inject a highly purified enzyme, a protein machine, directly into the patient's IV drip. This enzyme is designed with an active site that specifically targets and grabs free-floating asparagine in the blood and violently rips it apart using hydrolysis.
Wait, it acts like a microscopic terminator hunting down just that one specific amino acid in the blood and destroying it.
Yes. The enzyme circulates through the patient's body, completely eradicating all the asparagine in the bloodstream. Because the healthy cells can make their own internal supply, they survive just fine. But the leukemia cells, which rely entirely on scavenging it from the blood, suddenly find their supply cut off.
Wow.
Their protein assembly lines grind to a halt. They can't build new structures. The cancer cells literally starve to death, all because we injected a perfectly folded chain of amino acids to destroy their food supply.
That is just. It's science fiction happening inside the human circulatory system. We are using the rules of essential versus non-essential amino acids to starve a tumor. Okay, moving from medicine to industry. The next application is tanning leather. Animal hides are almost entirely protein. We chemically treat them to make leather for shoes, jackets, and sports equipment. So a leather jacket is basically just chemically hacked animal protein.
Specifically, it's mostly a protein called collagen. Collagen is the most abundant protein in mammals. It forms the connective tissue in skin, tendons, and ligaments. Structurally, collagen doesn't just fold up into a ball. 3 separate chains of amino acids wrap around each other to form a tight triple helix. It's like a microscopic braided steel cable.
Which is why raw animal hide is incredibly tough. But if you just left a raw hide out, bacteria would use enzymes to perform hydrolysis, break it down, and it would rot.
Exactly. Bacteria love to eat protein. So human industry invented tanning. Tanning is a complex chemical process where you soak the protein hide in specific compounds, traditionally plant tannins or modern chromium salts. These chemicals force artificial permanent cross-links to form between the collagen triple helices.
So it bonds them together.
It essentially welds the braided cables together into a massive, impenetrable matrix. The bacteria's enzymes can no longer access the peptide bonds to break them apart. You lock the protein polymer into a permanent, non-decaying state.
We are mastering molecular welding to make a durable jacket. Which brings me to the final major macro application we need to discuss, and this is the one that might actually ruin some desserts for you, the listener. Let's talk about gelatin. Bone matrix is heavily reliant on protein. Again, mostly that tough collagen cable. But obviously, bone is rock hard. What happens when we subject that biological structure to extreme heat and water? What happens when we boil an animal bone?
You perform thermal denaturation. Bone is incredibly hard because that braided collagen matrix is calcified. It is filled in with hard calcium minerals. But the underlying structure is still just folded chains of amino acids held together by hydrogen bonds and those sulfur crosslinks.
So when you drop those bones into a massive vat of boiling water,
the immense thermal energy of the boiling water causes the atoms in the protein chains to vibrate violently. It shakes them so hard that the weak hydrogen bonds holding the triple helix together snap. The braided cables unravel. The massive protein chains lose their specific 3D folded shape and open up into long, loose strings floating in the hot water.
But you haven't destroyed the peptide bonds, right? You haven't done hydrolysis to break the chain into single amino acids. You've just unraveled the sweater into a long piece of yarn.
Exactly right. You've denatured it.
Yeah.
But the primary chain remains intact. Now, here's where the physics of gels comes in. When you remove the heat and the water starts to cool down, those long, unraveled protein chains try to fold back up. But because they're totally scrambled and overlapping with thousands of other unraveled chains, they can't form their original neat triple helix. Instead, they tangle together in a massive, chaotic, microscopic fishing net.
And what happens to all the water they were floating in?
The water molecules get physically trapped inside the holes of this chaotic protein net. It forms a semi-solid colloid, a substance that holds its shape but is mostly liquid.
Wait, so when you eat a bakery item with gelatin, you are literally eating boiled animal bone protein.
You absolutely are. That chaotic water-trapping net is gelatin.
So when you eat a gummy bear, a marshmallow, or a beautifully glazed pastry, you are fundamentally eating the thermally unraveled, chaotic structural framing of a boiled cow or pig skeleton mixed with sugar.
You're leveraging the thermal denaturation of an animal's structural biology to give a jelly donut its satisfying, chewy texture.
It is the ultimate, slightly disturbing biological recycling program, but it perfectly illustrates the central theme of this entire journey. Whether you are looking at the intricate locks and keys of an enzyme curing blood cancer, the tough, welded matrix of a leather jacket, the chaotic, water-trapping net of a gummy bear, or the muscle fibers in your own heart responding to the electrolytes in an IV drip, you are looking at the exact same 20 biological building blocks. They are just shaped, folded, and manipulated by different biochemical or industrial processes.
It's the alphabet of biology, written in infinite variations.
Which brings us to the end of our deep dive. And I want to recap this journey not by just repeating what we've learned, but by using the Test Yourself 13.2 section from our source text as a framing device. Let's do a quick quiz for you listening at home. What elements are in proteins? Well, carbon, hydrogen, oxygen, nitrogen, and sulfur.
How are they bonded?
Peptide linkages formed by dehydration synthesis. What's the formula of an amino acid? You've got the amino group, the carboxyl group, and that unique R side chain, that little Lego accessory. And what does non-essential mean? It means your body's amazing internal factory makes it from scratch.
Which means every single time you move a muscle, brush your hair, digest a meal using enzymes, or even put on a leather jacket, you are interacting with the magnificent complex polymers of amino acids we've discussed today.
It makes you realize that you aren't just a separate entity moving through the environment. Your physical structure is an active, continuous continuation of the environment. Every time you eat a meal, digest it with enzymes, and use the raw materials to repair your tissues, you are participating in a multi-billion-year-old chemical legacy. You are a walking, breathing, constantly rebuilding cathedral of proteins.
A cathedral where the blueprints are shared by every living thing you can see out your window.
Exactly. And that leaves me with one final provocative thought for you to mull over. We've spent this entire deep dive marveling at the incredible diversity that arises from just 20 simple, microscopic Lego block amino acids. Nature takes this tiny modular alphabet and arranges it to create absolutely everything, from the incredible toughness of a rhinoceros horn to the softness of a bird's feather to a targeted enzymatic drug that can hunt down and starve cancer cells. It begs the question, if the staggering complexity of life on Earth is built on such a simple, elegant, modular foundation, what other incredibly complex systems in our vast universe might be hiding an equally simple foundational alphabet at their core, just waiting for us to discover it?
Now, that is a truly profound question to leave on.
Until next time.